Actually, Alicia An is associate professor at the School of Energy Environment, City University, Hong Kong, and leading water and membrane technology laboratory. Dr. An received her PhD in civil and environmental engineering at the Hong Kong University of Science and Technology. Before joining the City University, Dr. An was a project assistant professor at the University of Tokyo, Japan. Dr. An has been working in the field of membrane-based water treatment more than 15 years and published over 90 papers on emerging technologies such as membrane distillation, cold osmosis, and hybrid RO for removing emerging pollutants and resource recovery. Recently, Dr. An's research has primarily dealt with the fabrication of advanced superhydrophobic and omniphobic cross-polymer membranes, developing a fundamental understanding of and detection methods for membrane wearing, scaling, and fouling, and their practical application in MD through industry collaboration. She is currently one of the PIs of the theme-based research scheme in Hong Kong, entitled Paradigm Shifting Fully Integrate Compact Waste to Resource Facility, WWRF. Professor Ang, is you are here, yeah? Okay, so I pass over my mic to you. Your time.
So yeah, thank you very much.
So yeah, thank you very much, Shane, for your invitations. And it was very good to hear the previous speaker's talk on the SWRO. Hong Kong is currently constructing the first SWRO, and I think it will be ready in 2023. And so I think we have a lot of opportunity to have a research collaboration. So for the next 20 minutes of talk, I'd like to bring your attention from this pressure-driven SWRO to another type of thermal-based hybrid membrane process, which is the membrane distillations, and with a focus on new emerging material. It's kind of emerging material called the MXene. So we have engineered the MXene material to be used for efficient photothermal membrane distillation. So today my talk will start with a brief introduction of membrane distillation. As I said, this is different from the pressure-driven process, and how we have developed this the MXene material to be used for the solar-driven seawater desalinations. And recently we have engineered the system to couple with membrane distillations called the photothermal membrane distillations. So membrane distillation, well, we discussed the increasing water scarcity and the stringent discharge regulation, which I believe it associated the consideration of unconventional water resources such as seawater, hypersaline water, and wastewater. And these call for emerging technologies to successfully augment the water supply. And the membrane distillation thermally driven membrane process, so which is not affected by the salt concentration of the feed. So there is a reason recently it drew a lot of attention that as a promising technology for treating hypersaline waters that cannot be treated by pressure-driven reverse osmosis and traditional technologies. And since, although the MD is a thermal process, MD can be operated at a relatively low temperature, which gives opportunity to integrate it with waste heat or the solar energy as well. And also it can be operated at a low pressure, and also the produce high quality water. And I just want to show that this is our lab scale of MD process, and generated the permeate from the hypersaline wastewater. However, thermodynamically, membrane distillation process require large amount of energy to evaporate the water. So the typical enthalpy of vaporization can be 2 to 3 orders of magnitude larger than the Gibbs-free energy for the seawater desalination. So beside the energy consumption required for the vaporization, there are also temperature polarizations due to the convective and the conductive heat loss that need to be minimized to further improve the energy efficiency of the MD-based process, or not to mention the wetting and the scaling, the boundary issues. I'd like to also introduce the another angle that whether its membrane distillation can be coupled with the solar energy to reduce the energy consumption. So recently developed in the light to heat converting material have opened up the opportunities for efficient exploitation of the photothermal surface heating, which is kind of self-heating the membrane with low conductivity to maintain higher temperature gradient. So in general, the photothermal, the membrane generate this localized the energy transfer. And then the recent application in the solar steam generation and the photothermal MD has been introduced. So if I give you the simple the diagram to compare the standard membrane distillation process over photothermal MD process. So unlike the standard MD process, where we have to use the extensive amount of thermal energy to heat up the bulk feed water before it enters to the module, the photothermal MD utilize localized heating, as you can see here. So this localized heating induced vaporization of the feed stream directly at the membrane surface. So this significantly improved the energy efficiency of the process by eliminating the need of heating the entire bulk feed water and also reduced temperature polarizations. Reduce the temperature polarization. Then the issue is that whether we can develop this ideal photothermal membrane or membrane distillation that essentially possess the highly desired combination of a high photothermal conversion efficiency and as well as strong wetting resistance is the still a challenge. So in our study, we try to looking at some novel material, whether we can functionalize and enhance the membrane performance to be used in the photothermal process to increase the flux as well as prevent wetting. So thanks to the emergence of the various photothermal material, such as a semiconductor and the nanostructured carbon, and also the plasmonic the metal, as you can see here of the literature review, so there are various material has been used in the solar driven seawater desalination, starting from the gold and the carbon black and many different type of material. And then the recent the paper has also reviewed very significantly the use of different material. So in our study, we have looked into 2D metal carbide and the nitride called MXene. The reason we have we use this the MXene material is because it provides very broad solar spectrum absorption and also the outstanding photothermal conversion, and it has a very hydrophilic nature, so easy to self-stacking, and moreover, especially the unique, the localized surface plasma resonance LSPR effect of the MXene contribute largely to its excellent photothermal effect. So first, in our first study, we synthesize this MXene material and then generated the MXene nanoseed. So typically, this MXene nanoseed was synthesized through the selective etching of aluminum layer from the raw material, followed by the explorations in the deionized water. And as you can see from this figure of different characterization, that after this after we fabric synthesize the MXene nanoseed, we have characterized to make sure this MXene can give their unique feature of this photothermal effect. And then the first first study, we have actually tested this MXene nanoseed, whether it can be used in the solar thermal desalination. And but as I explained, because MXene is hydrophilic material, so the first step we have generated two phase of this hydrophilic layer by decorating this polypropylene layer on top of this the MXene layers. So the benefiting from those functional group and the size effect of MXene and the propylene can be uniformly self-assembled on the surface of the MXene. So we have made these two asymmetric wetting structure of hydrophilic and hydrophobic layer. So when we apply these solar thermal desalinations, so hydrophobic layer, upper layer is beneficial for heat localization and the self-salt resistance. And the hydrophilic bottom layer assure the efficient water pumping and the vapor transport. As you can see, this SMEs, this abandoned interlayer channel provide and increase this water vapor the transportations. So when we apply this the MXene nanoseed for the photothermal desalinations, and you can see here that the temperature increase, and also when we compare with, of course, PVDF membrane is not the photothermal, and this evaporation rate is high as 1.4 kilogram per hour per meter square, and the surface hydrophobic layer has a very good salt rejections, and also it provides a very stable water flux. So we have compared our study over the recent publications, and then taking the evaporation rate, efficiency, as well as salt resistibility into account, the obtained our the MXene membrane always were comparable to most of these membrane-based study which published in recent years. Okay, so after we successfully synthesized the MXene membrane from the raw material, and then the next step is we want to engineer the system with membrane dissipation. So as this is the design concept that from the conventional MD process, we use the noble membrane to use this solar radiance to increase the temperature at the membrane surface. Okay, so that is because of the MXene, the plasmon effect. And also, when we apply the membrane distillations, so anti-wetting is also one of the issues, and also how to convert this hydrophilic nature of the MXene to hydrophobic was also the question. And so in this work, based on our previous study of converting our also the architecture, the membrane surface to be hydrophobic or omniphobic, we have used our previous work, which is using the PDMS and mixed with this MXene powder. So the reason actually we use the commercial PVDF as a substrate is, well, we were able to make this the MXene layer with this inorganic membrane. However, the mechanical strength was not good enough to be used in the membrane distillation process. So we tried to find out the new method, which we can decorate this MXene layer into PVDF membrane to start with. Then, so first we synthesize this MXene powder and then mix with the PDMS to spray coating on the PVDF layer. So you can see here that the on the top of this commercial PVDF layer, we have spray coated this MXene, which is the engineered layer. So it has a dual function like previous solar desalination process, that this MXene layer provide a broad spectrum of the solar absorptions. So when we, during this optimization process, we can see that to maintain the high cross the membrane temperature gradient is due to the membrane with efficient photothermal effect, and which has a very high absorption rate and also the wide wavelengths. And when we utilize this, the MXene material into the membrane distillation, one of our concern is if it gives us very high thermal conductivity, because it is also it will hinder it will also induce the temperature polarization. Well, because of our coating method, and you can see here, compared to even this PVDF membrane, even though we has used the MXene material into our membrane, the thermal conductivity was even reduced compared to this commercial PVDF membrane. So the thermal conductivity was not of issues after successful optimization. And the temperature, well, this solar absorption was very good, and also within this 3 minutes, you can see the surface temperature was increased up to 85 degrees Celsius. And this is the image from the IR camera on this our PDMS and the MXene base of the membrane over commercial membrane, that how the temperature was increased on the surface. And also because we tried to architecture like a double and the re-entrance structures, which will induce the lower the thermal resistance, as well as increase the anti-wetting performance. And also this work is now under revision in the Nature Communications, and still we have to further optimize. And in terms of anti-wetting properties, and maybe many people will ask how this MXene hydrophilic how we can overcome this hydrophilic nature to be hydrophobic. So when we tested this, modified the MXene membrane for this anti-wetting property, actually we were quite surprised that the even this contact angle was increased up to 170, and it has a very super rolling effect. And this is kind of the image of this contact angle over different liquid, the liquid tension, and also it provided this water bouncing effect. So we have also tested our membrane with our homemade anti-wetting monitoring or scaling, and also fouling the monitoring, and it provided a good anti-wetting and also the scaling effect. And here is the flux data through this the impedance study, that it provided very stable wetting and flux. Well, and when we compare this the solar density over the flux, okay, under the different sunlight. Of course, when there is no sun, and the flux between this commercial membrane and our the MXene based membrane has almost no difference. But when under the one sun, you see that the MXene based membrane, the flux was increased up to 2.8 kilogram RMH. And of course, as a similar pattern, when there is the solar density increase, you can see that the MXene can absorb the more solar energy and increase the water flux. And also the flux, well, we have tested certain times, and it provides a very stable flux. And also this is the image that we have used the lab, very small scale of the lab scale photothermal MD process here. And also this is the IR camera image to monitor the temperature increase under the different solar solar densities. And then finally, we also have compared our study over different literatures. And we found that our study, the membrane outweighs the most of the photothermal membrane distillation membrane and the solar-derived interfacial water evaporators, and especially for hypersaline water treatment. So to conclude, so we have developed this MXene engineered membrane that impart efficient localized photothermal effect and the water repellence for sustainable photothermal membrane distillations. And the efficient solar harvesting capability of MXene enable photothermally localized surface self-heating of membrane is due to the to overcome the inherent heat loss at the feed site induced by continuous water to vapor transitions. And this high electrically conductive MXenes plays structural directing role for the self-assembly of uniform hierarchical polymeric nanospheres on which surface via electrostatic spraying and transforming the intrinsic hydrophilicity into superhydrophobicity. So benefiting from this interfacial engineering, the MXene-based membrane is endowed with constant high across the membrane temperature gradient, as well as a strong wetting resistance and rendering significant boost in the freshwater production rate. Our data shows up to close to 3 LMH, and the stability when treating hypersaline water, which was 10% of the salinity under one sun irradiations. Well, our work presents a very simple strategy on developing this well-performing MXene membrane for potential seawater desalination from the material perspective. However, the emerging MXene material membrane are still limited to the lab-scale research, and there is just a long way before achieving the large-scale application in the futures. And okay. Yes, so I think with this I will conclude my talk. And yeah, so this is the picture of our the group members. And recently we also developed some new material to participate in industry applications. And with this, thank you very much. And thank you very much for your attention.
Thank you very much. Nice talk, Professor Ang. Since we have a limited time, so we can receive the question. So if audience have any question, please leave your message in the chat box to directly Professor Ang. Maybe Professor Ang will reply one by one.